Alright guys, welcome back. So we're taking a look at 12.2 today, vectors in the coordinate plane. So we're going to get some actual math behind these vector questions. So first up is the component form. We find this by using the initial and terminal points, and that is important. The initial point is where it starts, terminal point is where the vector ends, because the component form of the vector will be terminal minus initial. If you do it the other way around, you are not properly getting the correct answer. In fact, you can get what's called the opposite vector, where it's just in the opposite direction. So here we want to find our component form, so our vector AB. We are doing our vector notation with that triangle brackets kind of thing. It's terminal minus initial, so it's 3 minus -4 and -5 minus 2. So we would get a +7, -7 for our component form of vector AB. Very straightforward subtraction. As long as you're careful with the correct order, not going to be that bad. Now, as for the magnitude, this is going to be how long the vector is. In fact, you're going to recognize this as the distance formula, because this form is the distance between 2 points. Magnitude of the vector is how long the vector is, which again, distance formula setup. If it's in component form with the a and b, then it's just simply the square root of a squared plus b squared, again, recognizing your Pythagorean theorem. So here we need to find our component form first. So we're going to go ahead and find a component form for this thing. So it's our 3 minus -4, -5 minus 2. It's the exact same thing we had just dealt with. So we got 7, -7. So then our magnitude of AB would just be the square root of 7 squared plus -7 squared, which is 49 plus 49, which is 98, which simplifies to 7√2. All right, so a lot of times you'll be asked to find component and magnitude of your vector together in the same question. If you're finding either one, just again go through that process. Now for some vector operations, we can add, subtract, and do a scalar multiplication of our vectors. Vector multiplication, where we multiply two vectors together, is a little bit different. That's going to get into the idea of dot and cross products, which we'll cover in 12.4 and 12.5. Put simply, vector addition subtraction is going to abstract the components of the vectors together. Scalar multiplication, you're going to distribute whatever the scalar quantity is to each piece of that vector. So if I want to find w plus y here, so w, we would have -4 plus 2 for the first two pieces of your vector, and then 1 plus 5 for the other two pieces, getting us -2, 6. For the addition of those two vectors. Now for z minus 2y, well, we have z first, so it'll be -3 minus 2 times y, so -2 times 2 there. And then comma, next component of z is 0, minus 2 times that, and the second component is a 5. So we're going to get a -7, -10 for the component form of z minus 2y. As long as you're careful with your basic addition, subtraction, multiplication, if there happens to be a scalar, it's really not going to be that terrible. Now we also have what's called a unit vector. This is a vector of magnitudes of 1 unit. So it's going to be going either in the same or opposite direction as the vector v that we're dealing with. The idea is we want to make it smaller, so make it shorter and deal with a magnitude of only 1. If we are in the same direction, we're multiplying by 1, so we're really not doing anything. But if it's in the opposite direction of whatever our vector was originally, then we got to multiply by a -1. So here we want the same direction. So our unit vector u would be based on -2, 3 divided by the magnitude of v. So the magnitude of v, we would do the square root of -2 squared plus 3 squared. 4 plus 9 is 13. We can't simplify that square root of 13, so we'd leave it like that. So this would be -2 over root 13, and then 3 over root 13. Which sometimes you can leave it in the unrationalized form. More often than not, though, you are going to have to rationalize that answer. So we would and get -2 root 13 over 13, and then 3 root 13 over 13. That would be our answer. Now, if they want it in the opposite direction, all we would do is multiply that u that we just got by -1. So we would say it'd be 2 root 13 over 13 and a -3 root 13 over 13. That'd be if I wanted the opposite direction rather than the same direction. Now, we don't need to use these triangle brackets to write our vectors. We also have what's called a linear combination, using what's called I and j. Not to be confused with I as this square root of -1, the imaginary number. It's being used to denote a positive x-axis direction with a unit vector. So I is 1, 0, j is 0, 1. They're also called standard unit vectors. So rather than writing our vector as AB, we can write as AI plus BJ. And sometimes, depending on the problem, they might prefer to be in a linear combination format. So we're going to write this as its component form first, and then put it into its linear combination form after that. So DE would be terminal minus initial, so 4 minus -2, and then 5 minus 3, getting us 6, 2. So the linear combination format, that would be 6i plus 2j. Just a different way of writing it. Going forward, I will give you either the component form, if I want you to work with the vector, or the linear combination form. You can use them interchangeably. Now, finally, we want to know the angle that the vector is going in, its direction angle. Well, you should recognize this formula. We've used this so many times for so many different things. But theta is the tangent inverse of b over a, where if a is positive, it's just tangent inverse of b over a, whereas a is negative, then we're going to add 180 degrees. Now, we're working with degrees here rather than radians, typically because a lot of times with vectors, it's going to make a little more sense to, even though degrees are not as mathematically accurate, it's a little more real-world uses. Telling someone you got 30 degrees between two things versus pi over 6 radians. A mathematician knows what pi over 6 radians is, but the average person can understand what 30 degrees is. That's what we're going to have more focus here. All right, so we're going to go through two different examples here, just to show you again when it's positive versus negative for the value of a. So for a, the direction of vector p, so theta p, would be the tangent inverse of 7 over 3. And you just use your calculator. Tangent inverse 7 over 3 makes sure you are in degrees mode. And we should be getting 66.80 degrees. So you don't necessarily need to write the 0 there. Since we're rounding to the hundredths place, we don't need the 0 if it's a 0. But if there was like another number, obviously we'd write that. Whereas for direction of vector r, it's still the tangent inverse of b over a, so -8 divided by -3. But because a is negative, we are going to add a 180 on there. If it was positive 3, -8, then we wouldn't, because again, we don't care about the b value being negative, we care about a being negative. So we go ahead and do that quick calculation. We're going to get an angle of 249.44 degrees. All right, so that's your basic math behind our vectors. We're going to do a couple more things. We're going to talk about three-dimensional vectors. The next one, we'll also get into the different multiplication possibilities of units, the dot product and the cross product. So I'll see you for next time for those videos.